Today we're going to look at finding position, velocity, and acceleration of a function using just basic calculus principles. So in physics, you have what is known as the kinematic equations, which is going to be the study of motion, and you have formulas such as what you see on the page right here. However, at the basic level of calculus, you only have one way of going from position to velocity to acceleration. I like to think of it as a ladder. At the top of the ladder, I have position. Then in the middle of the ladder, I have velocity. And at the bottom of the ladder, I have acceleration. Now, position at the basic level of calculus often is listed as s of t. They use s for position or distance. Velocity is a function of time, so that's v of t. And acceleration also is a function of time, which is a of t. Now, to go from one step to the other, rather than use all those physics formulas, in calculus, what we can do is just take the derivative to go step by step. So to go from position to velocity to acceleration, all I need to do is take the derivative. Now, if I'm trying to go from position down to acceleration, I have two steps in between, which means I'm going to have to take two derivatives, take the derivative of position to get to velocity, then take the derivative again to get to acceleration. And we're going to see that in the next example. So a lot of times these are going to be dealing with word problems. So this example says, use the position function s of t is equal to negative 16t squared plus v sub 0 t plus s of 0 for free-falling objects. And a ball is dropped from the top of a building that is 150 feet tall. Based upon that, we're going to calculate a couple different things. All right, where I would start is I would draw a picture. So we are given a building that is 150 feet tall. So here I have my building, and I can label that 150 feet. We have a ball that's being dropped from the building down to the ground. And so a couple of things you need to keep in mind. If we're dropping the ball from 150 feet, I'm not putting any speed behind that initial toss. It's not even a toss, it's just a drop. So the initial velocity, which normally we call VI, is going to be 0 feet per second. And when the ball gets to the bottom, here it starts at 150 feet. Down here it's going to be a height of 0 feet. Now, looking at my position equation, the position equation is s of t is equal to negative 16t squared plus v sub 0 t plus s sub 0. This v sub 0 is initial velocity, same thing as vi. So I know initial velocity goes to 0. So that whole middle term cancels out to 0. The initial height is going to be s sub 0, which is 150 feet. So in part A, when it says write the position function, I have s of t is equal to negative 16t squared plus technically 0t, so I don't have to write that, plus s sub 0, which is 150. That's my initial height there. And that's all it wants. Part B then says determine the velocity function for the ball. Well, based on what we had on the previous page, to go from position down to velocity, I have to take a derivative. So what I need to do is I need to figure out, well, what would be s prime of t, because s prime of t is equivalent to velocity, v of t. So this is where you use the power rule. Using the power rule here, I take my exponent, multiply in front, subtract 1 from the exponent. So the first term goes to negative 32t. And then 150 is a constant number. Derivative of a constant is 0, so plus 0 here, which we don't have to write. So velocity is just negative 32t. Nothing more than that. Now I want to determine the average velocity on the time interval 0 to 1. Average velocity has its own equation. It is given as the change of position, so change of s, over change in time. So I need to figure out what is the position at 1 second minus the position at 0 seconds over the change in time, which is 1 to 0 seconds, because this time interval over here is measured in seconds. In order to find s of 1 or s of 0, I need to go back to my position equation up here in part A and plug that in for t. So what I'm going to do is I'm going to take this t equals 1, plug it in for t here. So I'm going to have negative 16 times 1 plus 150 is that s of 1. So if I write that out, we have negative 16 times 1 squared is 1 plus 150. That's my s of 1 minus, now I plug in the 0, so negative 16 times t squared, t is now 0 squared, plus 150. 0 squared is still 0, so I don't really have to write the squareds there if I don't want to. All over 1 minus 0, which is 1. And then if I simplify that, I end up with 134 for the first set of parentheses, minus this goes to 0, plus 150, so minus 150 over 1. And 134 minus 150 is negative 16. And because we're talking about velocity here, that would be measured in feet per second for this problem. Since height was in feet, time was in seconds. Now the next part of the problem says, find the time required for the ball to reach ground level. When the ball reaches ground level, you have to keep in mind, it started 150 feet above the ground. So by the time that ball comes all the way down from the top to the ground, it has actually traveled 150 feet, and now my height is equal to 0 feet. So if I want to find the time that it takes for the ball to reach the ground, I need to go back to my position equation, which was s of t is equal to negative 16t squared plus 150. That came from part A. Set that equal to 0, which would be the final height, which is when it hits the ground. And then I'm just going to solve this for t. So I can add the 16t squared to the other side, then divide by 16. So t squared would equal 150 over 16, which gives me 9.375, or you can leave it as a fraction if you prefer. So I get t is equal to plus or minus the square root of 9.375, and if you evaluate that in your calculator, you end up with t is equal to plus or minus 3.062. Now, time cannot be negative, that doesn't work in real life, and so here I'm only going to include the positive version, so my final answer would just be time is equal to 3.062 measured in seconds. So the next thing I want to do is figure out what would be the velocity of the ball at impact. When the ball impacts the ground, we just found that the time of impact was 3.062 seconds. That came from part D, like I said. So if I want to find the velocity of the ball at impact, I already know how long it's going to take to actually hit the ground. What I can do is go back to my velocity equation, which came from part B. V of t, which is velocity, was negative 32t. All I need to do is just plug in this time in for t, and that'll give me the velocity at that time. So I have velocity at 3.062 is equal to negative 32 times 3.062, and you end up with negative 97.984 feet per second. Now keep in mind it is negative because the ball is traveling down, so velocity has to be negative there. And since it has fallen a little over 3 seconds, you would expect it to have a fairly high number for the velocity, so 97 is not unreasonable for this problem. Okay, last one says find the acceleration of the ball at impact. So now if I'm finding acceleration, think about your ladder. You had position, velocity, acceleration. To go from one step at the top to the next step, I took a derivative. Then to go from velocity to acceleration, we have another step. So I need to take the derivative of velocity to get to acceleration. So velocity was equal to negative 32t. That came from part B, and also we used it in part E. So if I differentiate velocity, we're talking about v prime, that is equal to acceleration. And the derivative of negative 32t is just negative 32. So acceleration for this problem is equal to negative 32. And that would be measured in feet per second squared. Now notice, it doesn't matter what time I'm plugging it in, so at impact was 3.062 seconds, but I can't plug in that t value because I do not end up with a t in my acceleration problem. That is because negative 32 feet per second squared is actually something very important, and that is negative 32 feet per second squared is acceleration due to gravity. Often you memorize acceleration due to gravity as negative 9.81, but that is in meters per second squared, so the negative 32 is measured in feet per second squared. And that is always going to be the same regardless of the time, because that is the rate that the Earth is actually causing the object to fall in terms of its acceleration.